Bismillahirrahmanirrahim. In today's video, we discuss about the origin of discontinuous conduction mode. So now we taken a circuit of such type that we apply voltage Vg, connect this voltage with a bidirectional MOSFET switch, and another switch is connected here, which is unidirectional diode, and this is the boost converter. So the inductor will be connected at the load side. And it is buck converter, so the inductor connected in at the load side, while in boost converter the inductor connected at this side. So now analyze this circuit for CCM, and in CCM we know that the conversion ratio which we get is equal to D, and it is equal to V0 by Vt. Vg, as I already discussed in my previous video. Now the inductor current ripple which we get, as we already discussed in continuous conduction mode, that ripple, let's suppose this is the I DC current, that ripple will be equal to such like Ts. This is the dTs, d dash Ts. Now this length is equal to del I, this length is equal to also equal to del I, so this whole length is equal to 2 del I. Now in order to find the inductor current, so we know that the 2 del I will be equal to dTs multiplied by slope. Now the slope here is equal to VL by L, where VL, this is the VL, so when this switch is on, then this Vg, and this switch is off, then this Vg come here, and here the output voltage is V0, so this voltage is V0, so VL become equal to V0 minus Vg or V minus Vg. So now putting that value here, so we get V minus Vg divided by L. So putting this value in equation 1, we get 2 del I equal to dTs V minus Vg divided by L. Now multiplying and dividing Vg, so we get 2 del I is equal to dTs divided by Vg into a mistake happened here, as this is VL is equal to Vg minus V0, because this is the buck converter, and in buck converter Vg always be greater than V0, so that's why we get VL is equal to Vg minus V0, not this. So putting this value here, we get Vg minus V0, this also equal to Vg minus V0, so this become equal to V0 by Vg, so 2 del I is equal to dTs Vg divided by L to 1 minus D, and that will be equal to 2 del I is equal to dTs Vg d dash divided by L. So del I current ripple will be equal to dTs divided by 2L Vg dash. So from this equation we know that the current ripple always depend upon all these terms and mainly on Vg. So we can control our current ripple through Vg. If we minimize the input current, then the current ripple will become smaller. Now we also know that this is the DC current, and DC current always go in load, not in capacitor, because it is DC and the capacitor does not allow DC current. So all the DC current flow in resistor, so the DC current will become equal to V by R. So from this equation you know that if you can control the DC current by output voltage and resistor, if you minimize the resistor value, so the DC current will become larger, and if you increase the resistance values, and then the DC current will become smaller. So let's see, if we increase the load resistance, then the current will become smaller and the graph will become such like. So we get such like of graph if we minimize the DC current value. So the DC current value becomes smaller by increasing the load resistor R. Now here you see that the inductor charge in this time and will discharge in this time never go to 0. So in full DTS, inductor charge and discharge. Now what happen if we further increase the DC current? So we get such like of graph. What it means? It means that if you switch on, when you switch on, then the all current flowing in this inductor and this inductor become energized. So as we here see that the inductor become energized. Now when we switch off this and on this switch, so what happen? This portion become separated, and the current, the inductor provide the current to the load, but the load is very high, so very small current flowing in this inductor, but the load is very high resistor, so this inductor current become de-energized in a very less time. As you see that the whole time is Ts here and here, in such minimum time we can say that the 2 Ts, the inductor current become de-energized, while before increasing load resistance we here see that this is the Ts, the charging of inductor is half of the time of the Ts, while similarly the discharge of the inductor energy is half of the Ts. But here the full time is this, the inductor charge in this time, but discharge in minimum time, in such minimum time. So why this minimum time? Because of the high resistor output resistance load, or high resistor output. So that high resistor output discharge the inductor in such a very minimum time, and that minimum time is G2 Ts. After that the inductor again want to be energized in opposite direction. Here the inductor again want to be charged in opposite direction. But here, due to the unidirectional switches, we get the such like of graph. This is DTS, this is D2TS, this is D3TS. So we get the graph of such like, because the diode doesn't allow the current in opposite direction. So that's why after discharging the whole inductor current, the inductor current ripple becomes 0 and for some time, and that time is D3TS. What happens if we connect the bidirectional switches here? Instead of diode, you connect the bidirectional switches. So what happens? In such a way, in such type of switches, we get this graph. In this portion, that MOSFET which we connect now allow the negative current and charge the inductor in opposite direction. Initially, when this switch is off and this switch is on, so it charge the current inductor in this polarity. But when this switch is off and this switch is on, let's suppose we connect this type of switch, bidirectional switch, then the inductor energized inductor become de-energized and through load resistance, so the whole current flowing in this way. Now what happen if we increase this load resistance? Then the inductor de-energized in a very small amount of time, and that small amount of time is equal to D2TS. Now after that, as we connect here the bidirectional switches, so this negative polarity come here, so this become minus and this become plus, so the inductor become charged in a negative direction. Although this switch is off for 1 minus D and this switch is on for 1 minus D, it is on and it is off, so this inductor charge negatively and that charge is this. And you know that the inductor depend upon current. The energy stored in this is directly proportional to I square. So inductor depend upon current. If we want to charge it negatively, so the current must be negative. So after in negative current, the inductor get charged but in negative direction. So here the inductor charged but in negative direction. So what happen after that? If we on the switch, this is the DTS. Then what happen? This switch become on and this switch become off. So this voltage want first de-energize this inductor energy. So for example, this is minus 6 and this is 8, so it de-energize first, so it becomes 0, and after that it go to 2. So it first de-energize and the inductor current gets 0, which is this, and then it energize the inductor up to 2 ampere, so it get energized up to 2 ampere. So the similar situation also occur after that it become de-energized. So now that's why we connect here the unidirectional switch, which is the diode. So it in 1 minus dt it become on and it de-energize the resistor load, but in after de-energization it doesn't allow the current in opposite direction, so that's why it doesn't charge in opposite polarity and the current becomes 0 in this diode. So that's why the current becomes 0 in this one, and this is the DCM. Now what happened to the ID? So in DTS, when this switch is on, then no current flowing in this diode, so the current in diode is 0. So the current in this is 0. After in D2TS, the diode get on and all the inductor get de-energized through resistor by following this path. So the inductor current become equal to this current. Similarly, after there is no current flowing, so that's why this current in D3TS no current flowing in inductor. So now here the DC current we get is here. So that is here. So now you see that this is del I. So here you see that the del I greater than I, and in upper region here, not here, this is I. For from origin to this is the I, and this is del I. So here the I is greater than del I. So we get another difference through which we can say that either this is DCM or in CCM. So if the inductor current ripple is greater than the DC current flowing in inductor, then that in such case that will be operate in DCM. While if inductor current ripple is less than the DC current flowing in inductor, that operate in CCM. So now I already find this thing, and this is equal to this value. So just putting this value here, we get DTS divided by 2L VG T dash is greater than, let's do for it, and that current is equal to V by R. So putting that value here, so we get V by R, and we know that in buck converter the V by Vg become equal to D. So putting that value here, so we get Vg D divided by R. So Vg become cancel out with this, D cancel with this, so we get Ts D dash divided by 2L greater than 1 by R. So now simplifying it, we get T dash greater than 2L by R Ts, or D dash into tau by Ts, as in inductor tau is equal to L by R. So we get this equation after simplification. So now this R is the constant, so we give another name for it is equal to K, and this is equal to K critical. So K critical is greater than K. So you can say that if K is less than K critical, then that will operate on DCM, while if K is greater than K critical, then that will operate in CCM. And this K, as we know that the K is equal to 2L by R Ts, while the K critical is equal to D dash, which is equal to 1 minus T. So from here, when after building a circuit or making a circuit, you have a fixed value of L, a fixed value of R, and a fixed value of Ts. So this is constant, and it is also unitless. How unitless? As we know that tau is equal to L by R, and its unit is in second. So this is the tau become equal to the unitless L by R. So this unit is second, so 2 second by second, so it becomes 2, so unitless. So now we get a condition that if k is less than k greater, then that will be in DCM, and if k is greater than k greater, that will be in CCM. And also, if you increase the output load resistance, then k become equal to smaller than the critical value, so that will operate in DCM. And while the critical value is depend upon the duty cycle 1 minus t. So now let's plot it. So what will happen? Let's plot it on D. So at D equal to 0, we know that the D is 0, 1, so D equal to 0, so we get k critical. So let's suppose this is the inductor current ripple. So here the k is greater than k critical. Now it's not k critical, it is just k, because k is constant. So we get a fixed value of k, 2L by R ts. It is the constant, so this is the k, and the critical value of k depend upon the duty cycle. So this k critical vary with duty cycle. So here the k is less than k critical, and in this portion k is greater than k critical. So here it operates in DCM, and here it operates in CCM. Okay, so now if you further increase this k value, and the inductor current which you get is in this, so this such type of circuit operate always in, here it is k, this is the k critical, and k is greater than k critical, CCM, as this condition is for CCM. So now what is the relation? Let's see with the load resistor relation. So we know that k is inversely proportional to load resistor. So we can say that if R is greater than R critical, so that will operate in DCM, and if k R is less than R critical, then that will operate in CCM. Just opposite to k. Here the k is less than k greater, and the k is greater than k critical. So this is all about the origin of discontinuous conduction mode.